AI is changing the way engineers work. From requirements and calculations, to CAD, simulation, testing, and design reviews, each stage has different opportunities and different limits. In this video, we'll connect those pieces into one engineering workflow. By the end, you'll see how these individual capabilities can be combined into a structured engineering workflow, and where AI can genuinely improve engineering productivity without compromising engineering judgment. A large language model is fundamentally a probabilistic sequence model. It predicts tokens based on patterns learned from its training data and the context provided to it. It does not perform a free body diagram in the same way an engineer does. It does not automatically know whether a particular edition of a standard is applicable. And it does not have a physical connection to your machine. So when an AI gives you an engineering answer, you should not ask, "Does this sound correct?" Ask, "What evidence supports this answer?" That changes everything. AI output should be treated as a hypothesis, not as engineering approval. The verification chain remains. AI, then engineering calculation, then validated simulation, then testing where required, and finally, engineering judgment. This is probably the biggest change I would recommend. Don't start with, "Design a hydraulic cylinder mounting bracket." That is a poor engineering prompt. Instead, define the engineering problem. For example, I am designing a welded hydraulic cylinder mounting bracket. The maximum cylinder force is 180 kilonewtons. The cylinder pin diameter is 60 millimeters. The bracket is fabricated from S355 structural steel. The machine experiences cyclic loading. The design life is 10 years. Identify the critical load paths, potential failure modes, required calculations, missing information, and applicable verification methods. That is a much better interaction. Mechanical engineering is not just calculation. It is problem formulation, and AI can be extremely useful at that stage. One of the most underrated applications of AI is requirements analysis. Consider a requirement like, "The boom shall be sufficiently strong." That is not an engineering requirement. It is an intention. AI can help convert that statement into measurable engineering parameters. For example, maximum operational load, maximum abnormal load, load direction, design factor, allowable stress, maximum deflection, fatigue life, operating temperature, corrosion environment, design life, inspection requirement, verification method. Now the requirement becomes something that can actually be verified. This is where AI can help bridge the gap between natural language requirements and engineering verification criteria. This is one of my favorite applications. Give AI the design problem, and ask, "What information is missing before this problem can be solved reliably?" For a structural component, the answer might include boundary conditions, load spectrum, dynamic amplification, material condition, weld category, joint geometry, manufacturing process, environment, fatigue requirement, and inspection method. For a hydraulic system, it might ask about maximum pressure, rated pressure, pressure spikes, flow rate, fluid viscosity, temperature range, hose configuration, valve response, and cylinder geometry. This is valuable because engineering errors often originate, not from bad mathematics, but from bad assumptions. AI can help expose those assumptions early. Now let's use AI differently. Instead of asking, "Is this design good?" tell it, "Try to break this design." Give AI the design description. Give it the loads. Give it the material. Give it the operating conditions. Then ask, "Identify every credible failure mechanism." For a welded structural bracket, you might get gross yielding, local yielding, plate buckling, weld failure, pin shear, pin bending, bearing failure, tear out, fatigue cracking, stress concentration, and unintended load transfer. Now the engineer investigates each mechanism. This is similar to an adversarial review. The AI is effectively trying to find weaknesses in your engineering argument. And this can be particularly useful before a formal design review. Let's take a simple example. Suppose a hydraulic cylinder produces 200 kilonewtons of force. The cylinder bore is 100 millimeters. The basic piston area is A equals pi d squared divided by 4. That gives approximately 7,854 square millimeters. If the hydraulic pressure is 250 bars, the theoretical extension force is approximately 196 kilonewtons. But real engineering does not stop there. We need to consider pressure losses, rod side area, seal friction, dynamic effects, pressure spikes, temperature, and the actual hydraulic circuit. This illustrates an important point. AI can help establish the calculation structure, but the engineer must understand the physical model. The model determines the result, not the language model. Here is a very simple but powerful technique. Whenever AI gives you a calculation, check the units. Suppose AI calculates force using F equals pressure multiplied by area. Pressure has units of newtons per square meter. Area has units of square meters. Therefore, newtons per square meter multiplied by square meters gives newtons. The dimensions work. If the units do not work, the calculation is wrong. This sounds elementary, but dimensional analysis is one of the simplest ways to catch plausible-looking AI errors. For more complex calculations, also check limiting cases, order of magnitude, sign convention, conservation laws, and sensitivity to the input parameters. These are engineering sanity checks. This is where things become significantly more powerful. Imagine you need to calculate structural stress for 500 load combinations. Doing this manually is not engineering productivity. You should automate it. AI can help you generate the initial Python implementation. For example, input load, geometry, material properties, boundary condition, safety factor. Then calculate reaction forces, bending moments, axial loads, shear forces, stresses, deflection, and utilization ratio. The important point is this: don't ask AI to calculate one answer. Ask AI to help you create a repeatable calculation pipeline. Then validate that pipeline against hand calculations. Once validated, you can reuse it. That is where the productivity gain becomes substantial. Now suppose your component has 4 design variables: plate thickness, gusset thickness, bracket width, pin diameter. Instead of evaluating one design, we can generate hundreds. For example, plate thickness, 8, 10, 12, 16 millimeters. Gusset thickness, 6, 8, 10 millimeters. Pin diameter, 40, 50, 60, 70 millimeters. Python can generate the combinations. An analysis solver evaluates them. The results are stored in a dataset. Then we can examine mass, stress, deflection, fatigue utilization, manufacturing cost, and safety factor. Now the problem becomes an optimization problem. We are no longer asking, what design should I choose? We are asking, which region of the design space satisfies all constraints with the lowest engineering penalty? That is a much more sophisticated engineering workflow. There is another interesting application. Suppose running one fee simulation takes 20 minutes. Now imagine you need 5,000 simulations. That would take far too long. Instead, we can generate a smaller set of high-quality simulation results. Then use machine learning to build a surrogate model. For example, inputs, plate thickness, load, geometry, material, and boundary condition. Output, maximum stress. The machine learning model approximates the relationship between inputs and output. Once validated, the surrogate can evaluate new design combinations almost instantly. This allows engineers to explore a much larger design space. But there is an important warning. A surrogate model is only reliable within the region represented by its training data. Extrapolation can be dangerous. So again, AI accelerates engineering. It does not remove engineering validation. Now let's move into CAD. Suppose your organization has 500 variants of a mounting bracket. The geometry is similar, only a few parameters change. Manually editing every model is inefficient. AI can help generate automation scripts for NX-Open, Creo Toolkit, SolidWorks API, Fusion 360 API, or other CAD interfaces. The engineer defines the design rules. The script controls the parameters. For example, length, width, thickness, hole diameter, hole spacing, fillet radius, and mounting pattern. Now one validated design logic can generate multiple configurations. This is much more useful than asking AI, create a bracket. The real value is AI plus rules plus CAD automation. This is an important concept. A prompt tells AI what you want. A design rule tells the system what must never be violated. For example, minimum edge distance equals 3 times the hole diameter. Minimum weld throat equals a specified value. Maximum plate slenderness must remain below a limit. Minimum clearance must be maintained. Specified material grades only. Specified fastener classes only. If the AI-generated design violates a rule, the workflow rejects it. This is much closer to real engineering automation. We are moving from AI, design something, to generate candidates subject to these engineering constraints. That is a major difference. Now consider a manufacturing drawing. An AI-assisted checking system could potentially inspect missing tolerances, inconsistent dimensions, material mismatch, BOM inconsistencies, incorrect part numbers, missing surface treatments, weld information, revision inconsistencies, and potentially conflicting notes. But there is a critical distinction. This is a pre-check. It is not the formal drawing approval. Think of AI as another reviewer looking for obvious inconsistencies before the drawing reaches the final approval stage. That can reduce the number of errors reaching manufacturing. This is another area where we need to be careful. Never simply ask a general AI model, "What does ISO 4413 require?" and use the answer as your compliance evidence. Instead, use a controlled document source. The ideal architecture is approved standard, document retrieval, relevant clause, AI interpretation, engineer verification. This is where retrieval augmented generation, or RAG, becomes useful. The AI retrieves the actual source material. Then it explains the requirement. The engineer verifies the clause and applicability. This is significantly safer than relying on the model's internal knowledge. Now imagine connecting AI to your organization's engineering knowledge. Previous design reports, approved drawings, test procedures, failure reports, ECNs, material specifications, supplier data, lessons learned, design guidelines, manufacturing deviations, inspection reports. Now an engineer could ask, have we previously experienced cracking in this type of bracket? The AI could search historical records. Perhaps it finds 3 previous failures, 2 related to weld toe cracking, and 1 associated with an incorrect load assumption. That information is extremely valuable. Because engineering organizations often have enormous amounts of knowledge, but it is trapped inside documents. AI can become an interface to that knowledge. Consider a failed component. You have photographs, fracture location, material certificate, manufacturing history, operating hours, load data, inspection reports, and previous failures. Don't ask AI, what caused the failure? Instead ask, generate competing failure hypotheses. For each hypothesis, identify supporting evidence, contradictory evidence, and the next test required to discriminate between the hypotheses. For example, Hypothesis 1. Fatigue initiated at the weld toe. Evidence required: fractography, weld profile, stress history, and crack propagation pattern. Hypothesis 2. Overload. Evidence: plastic deformation, load event history, and material yield behavior. Hypothesis 3. Manufacturing defect. Evidence: NDT results, weld procedure, porosity, lack of fusion or inclusions. Now AI becomes a reasoning framework. The engineer remains the investigator. Let's take a hydraulic system. The architecture contains pump, pressure relief valve, directional control valve, cylinder, hoses, filters, sensors, and control logic. AI can help create candidate failure modes. For example, pump failure, valve sticking, hose rupture, filter blockage, sensor failure, pressure loss, overpressure, internal leakage, external leakage. Then map cause, failure mode, local effect, system effect, machine-level consequence, detection method, and mitigation. This creates a structured starting point for FMEA. But again, the final severity and risk classification must come from the engineering team. This is an area where mechanical engineers can gain enormous value. Consider a prototype machine. You have sensors measuring pressure, temperature, force, position, velocity, motor current, vibration, and cycle time. Instead of manually reviewing the data, build a pipeline. Sensor data enters Python. Python cleans the data. Signals are synchronized. Outliers are identified. Derived parameters are calculated. Then AI can help interpret patterns. For example, identify operating cycles where hydraulic pressure exceeded the expected envelope. Or, compare cylinder extension time across all test cycles. Or, Identify conditions associated with abnormal vibration. This creates a bridge between physical machine behavior and engineering analysis. Now we can take this further. A digital twin is not simply a 3D model. It is a computational representation of the physical system connected to operational data. For example, machine model, physics model, sensor data, operational state, historical behavior. AI can then help detect deviations. Suppose the expected hydraulic pressure at a certain operating condition is 250 bars. But over several hundred cycles, the pressure required to achieve the same actuator performance gradually increases. That trend may indicate wear, increasing friction, internal leakage, or another developing condition. AI can detect the pattern. Engineering analysis determines the physical mechanism. This is where mechanical engineering and machine learning intersect directly. Suppose vibration amplitude is 2 mm per second today. Then, 2.2, 2.5, 3.1, 3.8, 4.6. The absolute value might still be below the alarm threshold, but the trend is changing. A machine learning model can detect the deviation from normal behavior. The engineer then investigates bearing condition, alignment, lubrication, imbalance, structural looseness, or resonance. The important concept is AI detects patterns. Physics explains them. Now let's move to a less technical, but very practical application. Mechanical engineers constantly translate information between different groups. A design engineer may discuss stress concentration, fatigue, load paths, and tolerances. A manufacturing engineer may care about weld sequence, accessibility, fixture requirements, machining, and cycle time. A project manager wants cost, schedule, risk, and milestone impact. A senior executive may need problem, impact, decision, and required action. AI can convert the same technical information into different levels of abstraction. That is not merely writing assistance. It is technical information compression and transformation. Consider an engineering change. A drawing changes, but what else changes? BOM, manufacturing process, supplier specification, inspection plan, test procedure, service documentation, spare parts, cost, schedule, compliance. AI can help identify potential downstream impacts. For example, if this material changes from grade A to grade B, identify every engineering artifact that may require review. That can generate an impact analysis checklist. The engineer then verifies the actual affected items. This can significantly reduce missed dependencies. Now we reach the more interesting part. A chatbot waits for you to ask a question. An agent can execute a workflow. For example, you provide an engineering requirement. The system retrieves the relevant specifications, checks the document revision, extracts design constraints, runs a calculation script, generates candidate parameters, calls a CAD automation tool, runs an analysis, collects the results, checks predefined design rules, and produces a review package. At the end, the system doesn't automatically approve the design. It says, here are the candidate designs. Here are the assumptions. Here are the calculations. Here are the violations. Here are the unresolved issues. Engineering approval required. That is a much safer architecture. For safety-critical engineering, human in the loop is essential. The system should know where it is allowed to act, and where it must stop. For example, AI can retrieve standards. Yes. AI can generate preliminary calculations. Yes. AI can run a Python script. Yes. AI can generate CAD variants. Potentially yes. AI can select the final safety-critical design without review? No. AI can approve a structural component? No. AI can certify compliance? No. The system must have clearly defined authority boundaries. I would divide AI adoption in mechanical engineering into 4 levels. Level 1, Assistant. AI helps with research, documentation, summaries, communication. Useful, but limited. Level 2, Engineering Copilot. AI helps with requirements, design reviews, calculations, FMEA, test planning, and technical analysis. Much more useful. Level 3, Tool-Connected Engineering. AI connects to Python, CAD, FEA, PLM, databases, test systems, and controlled documents. Now we have real workflow automation. Level 4, Engineering Agent. AI orchestrates multiple engineering tools, while operating within predefined engineering rules, with human approval at critical decision points. This is where engineering productivity could change significantly. If you are a mechanical engineer, you don't need to become a machine learning researcher. But you should understand the fundamentals. Start with LLMs, tokens, context windows, embeddings, vector databases, RAG, function calling, agents, model evaluation, hallucinations, data security, and AI limitations. Then learn Python, not advanced software engineering, just enough to read data, process data, perform calculations, create plots, build engineering utilities, call APIs, and automate repetitive tasks. Then learn how your engineering software exposes automation interfaces. NX Open, Creo Toolkit, SolidWorks API, MATLAB, Python-based simulation workflows, or whatever tools your organization uses. That combination is powerful. Mechanical engineering knowledge, plus computational thinking, plus AI literacy. If I had to choose only one skill, I would choose this: engineering decomposition. Take a complex problem and break it into smaller verifiable problems. For example, machine performance, power requirement, torque, speed, gear ratio, shaft loading, bearing loads, structural loads, fatigue, thermal behavior, testing. AI becomes much more useful when the engineering problem has been decomposed properly. Poorly defined problem, plus powerful AI, still produces poor engineering. Well-defined problem, plus AI, can produce a very powerful workflow. There is a useful way to think about this. Traditional engineering productivity is approximately engineer plus engineering tools. The emerging model is engineer plus I plus engineering tools plus data plus automation. The engineer remains at the center. AI increases the bandwidth between the engineer and the tools. That means the engineer can investigate more alternatives, run more calculations, review more data, explore more design space, and spend less time on repetitive cognitive work. There are some things we should deliberately protect. Engineering fundamentals, first principles reasoning, free body diagrams, hand calculations, physical testing, design reviews, failure investigation, standards interpretation, manufacturing understanding, and engineering accountability. If AI generates a 40-page calculation report, but you cannot explain the first equation, you have not become a better engineer. You have simply outsourced your understanding. That is dangerous. The mechanical engineer of the future may look different from today's engineer. Not because mechanical engineering disappears, but because the engineer's toolset expands. Imagine an engineer who can define a problem, query thousands of engineering documents, write a Python calculation, generate CAD automation, run simulations, analyze test data, build a small machine learning model, and orchestrate AI agents, while still understanding mechanics, materials, manufacturing, hydraulics, fatigue, thermodynamics, and machine behavior. That combination is extremely powerful. So, how should a mechanical engineer use AI? Don't use it simply to write faster. Use it to think through problems faster. Don't ask it to replace calculations. Use it to automate calculations. Don't ask it to make engineering decisions. Use it to expose assumptions and alternatives. Don't use it as an uncontrolled source of standards. Connect it to controlled engineering knowledge. Don't ask it to design one component. Use it to explore an entire design space. Don't ask it, is this design correct? Ask, what could make this design wrong? That is a much better engineering question. And perhaps the biggest shift is this: the competitive advantage will not belong to engineers who know the most AI terminology. It will belong to engineers who can connect engineering fundamentals, AI, computation, simulation, data, automation, and real-world machine behavior. Because AI can generate possibilities, simulation can evaluate them, data can reveal patterns, automation can execute the workflow. But ultimately, someone still has to understand the machine. Someone has to understand the physics. Someone has to decide whether the result makes sense. And someone has to take responsibility for the engineering decision. That person is the engineer. The future isn't AI replacing mechanical engineers. It is mechanical engineers using AI to become much more capable. Don't compete with AI. Build your engineering workflow around it. Learn the physics, learn the computation, learn the AI, then connect them.